3.1, quadratic functions and models. Okay, so looking at quadratic functions, we're going to start out with our basic polynomial function. If you remember, polynomial functions f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x to the 1 or x plus a sub 0. So this would be a polynomial function, and that would not be how you spell polynomial, not at all. So a polynomial function where n is the degree of the polynomial, a is the leading coefficient, a sub n, let me just put that so it looks more like a sub, a sub n, x to the n is the leading term, and a sub 0 is the constant term of this polynomial function. Well, we want to deal with quadratic functions, which means that we have f of x is equal to, we could say a x squared plus bx plus c. So simplify it down to where now it's a quadratic or a second degree polynomial. And the simplest form of a quadratic function is just f of x is equal to x squared. And you remember that as one of our standard functions that we learned about so that we could work with translations and things of that sort. So that's our base function, f of x is equal to x squared, and then doing different transformations to it puts it into these additional states where we have a, b, and c. Obviously, a cannot be equal to 0 because if you do that, you no longer have a quadratic function and you end up just having a linear function. But b and c can be equal to 0. And a can be equal to 1, in which case we have f of x is equal to x squared. Now, anytime you have the base function f of x is equal to x squared, you're dealing with a parabola. And if it's a function, that parabola either opens up or opens down. Now, a parabola or the x squared function is not one-to-one. Let's just make that clear. It's not one-to-one, it fails the horizontal line test, but it passes the vertical line test. So we can have that. Anytime we're dealing with the parabola, or when we're dealing with, well, let's go specifically to this case, when we have f of x is equal to x squared, remember that our domain is going to be from negative infinity to positive infinity, and our range for the x squared function, or our starting range when we start looking at what happens to it due to transformations and such, is from 0 inclusive to infinity. So that's our domain and our range. And we also should remember that from negative infinity to 0, the function is decreasing, and from 0 to positive infinity, the function is increasing. So just some things to keep in mind about this parabola x squared. Now as we deal with that, we should also remember that a parabola, and I'm just going to put here, a parabola is symmetric. Symmetric about what? Well, if it's just the basic parabola x squared, symmetric with respect to the y-axis. If it's not that base parabola, then it will have what's called the axis of symmetry. So I'm going to get rid of this and just say this vertical line here is the axis of symmetry. So the axis of symmetry, which means that you can fold this parabola over on that line, and it's the same on both sides. This point here is the vertex. So the vertex is either the minimum or the maximum value of a parabola. At least if we're dealing with a parabolic function, a quadratic function, it's the minimum or maximum value of the parabola. If we have our x squared, the base function, then it's the minimum value. But if this was negated and we had negative x squared, then it would be the maximum value because it would get flipped over the x-axis. Okay? So these are very important things to know about our parabolas. Where's the vertex and what is the axis of symmetry? So we're going to want to be able to find that when we are dealing with parabolas. Let me get this out of the way. Okay, so now that we have that out of the way, we can start looking at these a little bit and say, okay, well, what if we want to graph a parabola, and not just the x squared, but we want to graph a quadratic function, which we know a quadratic function is just a parabola that's been shifted around, that base x squared that's moved around. So when we do that, we can get the parabola into this form. F of x is equal to a times x minus h squared plus k, where the vertex of that parabola is at the point hk. And the axis of symmetry is at x equal to h. Because remember, we're dealing with parabolic functions, so it's going to open either up or down. Okay? Some things to note: if a is greater than 0, so if a is positive, then it opens up. If a is less than 0, so it's negative, then it opens down. Which makes sense because we know that x squared is a parabola that opens up, and a ends up just being a multiplier, right? That's doing a stretch or shrink. And if it's negative, that's just flipping it over the x-axis. So it's going to make that happen. Also, if the absolute value of a is greater than 1, then we have a vertical stretch. And if 0, oops, that's not 0. If 0 is less than the absolute value of a is less than 1, so a ignoring its sign is between 0 and 1, we have a vertical shrink. So no surprise there. X minus h, if you remember, when you act on the input, that's going to give you a horizontal shift. So if, in this case, if h is positive, it's going to be a shift to the right. If h is negative, it's going to be a shift to the left. And plus k is a vertical shift. So if k is positive, it shifts up. If k is negative, it shifts down. So we can say h greater than 0, shift right by absolute value of h. If h is less than 0, shift left by the absolute value of h. If k is greater than 0, then we shift up by k, and just for sake of completeness, absolute value k. And if k is less than 0, we shift down by the absolute value of k. So there we go. So a lot of bits and pieces of information here. The key thing being, we want to get into this form because it is going to give us the vertex, which the vertex by definition also gives us the axis of symmetry because the vertex is always going to be on the axis of symmetry. So the x value of the vertex is going to tell us the axis of symmetry. Okay? So, the question is, how do we get our quadratic function into this form? And I'm going to get this out of the way. Actually, I'm going to move everything over a little bit just so it's not in our way here. So we have f of x is equal to a x minus h plus k. The vertex is at hk, and the axis of symmetry, just going to save myself effort by just saying axis sim, is x equal to h. So I just want that up there, but I want it out of the way so we can do some work. So, how are we going to do this if we have something in the form f of x is equal to ax plus x squared plus bx plus c? Because that's not the same as that form. So we want to get it into that form. And the answer is completing the square. I know, you'd hope that we wouldn't see that again. You'd determine, okay, once we did completing the square, then we could just deal with the quadratic formula because we found that the quadratic formula was just completing the square. Well, unfortunately, such is not the case, so we're going to use completing the square. So that's excellent. Now, two different ways we can do this. One is the easy way. If a is equal to 1, then it really simplifies completing the square. Because remember, the first step of completing the square was to get rid of the leading coefficient or turn the leading coefficient into 1, so divide by it. Now, that sounds like a great idea until you realize we don't have a quadratic equation we can set equal to 0. We have a quadratic equation set equal to essentially y. So we can't just divide by it. It's not going to work for us. So let's start with an example where a is equal to 1 and see what happens there. Then we'll go into an example where a is equal to something other than 1. So let's say we have f of x is equal to x squared plus 2x minus 5. Okay? So we've got this here, and we want to get it into that form. And we're going to use completing the square. Well, we don't have a leading coefficient other than 1, so that's good. We don't need to divide. So basically, we need to complete the square with this portion here. So f of x is equal to x squared plus 2x, and I'm going to leave some space here, minus 5. Now remember when we were dealing with completing the square previously, we would add that 5 to both sides, and then we could plug in we could find what we needed to be our constant, and we would add that to both sides, right? But we can't do that right now because we only have one side to work on. So this is still on the same side. What we're going to do is just say, okay, x squared plus 2x, we want half of 2, which is 1. We want to square it, so plus 1. That completes the square here. But we can't just add 1 to the equation. We also need to subtract 1. Because 1 plus 1 minus 1 is 0, so we haven't changed the equation. But now that we have this, we have f of x is equal to x plus 1 squared, and then minus 1, because that's this portion, right? Minus 1 minus 5 is minus 6. So we can see that we're really close to the formula that we want to have. We have a is equal to 1, but we have x plus 1. So f of x is equal to x minus negative 1 squared minus 6. Now, I've said it before, whether you leave it here or switch it to this really is not critical. But when you want to start pulling the vertex and the axis of symmetry out, doing this may help to eliminate, we'll just say, oopses. Okay? But now we are in the form, and actually we probably, when we did that, since we were doing that, we should have done this. That was minus 6, so plus negative 6, right? To make it fit our form. A times x minus h plus k. A, which is 1, times x minus h plus k. So now we know that the vertex is at the point negative 1, negative 6, and therefore the axis of symmetry is at x equal to negative 1. And there we go. So that wasn't as painful as we might have expected it to be. But remember, completing the square is relatively easy when you have a leading coefficient 1, because it's just a matter of quickly going through it. It's when you have some other leading coefficient that tends to throw things off a little bit. So let's do one of those. And yes, I'm still leaving this up here because I want to remember where we're coming from and why we're doing this. So let's try this. F of x is equal to 2x squared plus x minus 6. Okay, so now is where it gets a little bit more interesting, because the first thing we would do with completing the square is we would divide through by this 2. But we can't really do that, because the only reason you can do that is because you would do it on the other side. We can't switch over to f of x divided by 2. So what we're going to do is, rather than that, we're going to undistribute that leading coefficient, meaning we're going to do this. F of x is equal to 2 times. So if I pull that out of these two, and remember, we're going to move this off, so I'm just going to pull it out of these two. Then that leaves me with x squared plus 2x squared minus divided by 2 is x squared. X divided by 2, okay, so we can do that as x divided by 2. Or 1/2 x minus 6. So we just pulled it out of those two. We didn't bother pulling it out of this one because really we don't want to worry about that one, because we want that out of our completed square. So now f of x is equal to 2 times x squared plus 1/2 x. Well, we need to finish this off, so we need to take half of 1/2, which is 1/4, and square it, which is 1/16, plus 1/16. And we still got this negative minus 6 out here. And then remember, what we did last time was, since we added 1/16, or we added some value here, whatever it took to complete the square, we then subtracted it to compensate for it. What we have to be careful with here is this 1/16 is being multiplied by this 2, whatever a was. So when we subtract it here, we have to distribute that through. So 2 times 1/16 is 2/16, so minus 2/16. Because we added not just 1/16, but 2 times 1/16, giving us 2/16. So now that we have that, we have f of x is equal to 2 times Well, this is x plus 1/4 squared. And then over here I can say, well, that's 2/16 is 1/16. So we have minus 2/16 is 1/8. Minus 6 1/8. So the only other thing we want to do is put this into that form. So f of x is equal to 2 times x minus negative 1/4 plus negative 6 1/8. And now we can find the vertex, which is negative 1/4, negative 6 1/8, and the axis of symmetry is x equal to negative 1/4, because we're in that form and we see that it's positive, which means that it opens up. And we have the vertex and the axis of symmetry. So not quite as bad as you might have thought it was going to turn out to be. Yes, it takes a little bit of effort there, but that's okay. But what about the domain and range? Because that's a good question with this. Well, what does this do to our domain and range? Well, simply put, we can look at our vertex to determine the range. Well, vertex and whether it opens up or opens down. And since it's a parabola, we know the domain stays the same, negative infinity to positive infinity. So domain, negative infinity to positive infinity. The range, remember the range is going to be from the vertex either to positive infinity or from negative infinity to the vertex. It just depends on whether it opens up or down. We said here this is positive, so it opens up. And if it opens up, then the vertex is going to be the minimum value. So our range is going to be from negative 1/4 inclusive to infinity exclusive. So negative 1/4 inclusive. Remember, the vertex is always part of that range. So that's going to be included, but negative infinity or positive infinity are never included because they're just concepts. Okay, so, but that's the process. We're going to take a function in standard form and we're going to complete the square to get it into our special parabolic form where we can read the vertex, the amplitude, and that gives us the axis of symmetry, tells us whether it opens up and down, up or down, what the vertex is, etc. Now I'm going to leave that up here again because we're going to look at the vertex formula. And what the vertex formula is basically it's a way for us to take the quadratic formula, the quadratic equation in standard form and find the vertex. Now to do that, we can perform completing the square again. So I'm going to do that for you, and you probably will never have to do it algebraically again, but you might, depending on what courses you're taking. So I'm going to take f of x is equal to ax squared plus bx plus c. I need to pull out a, so f of x is equal to a times x squared plus b over a x plus c. F of x is equal to a times, well now we have to get the constant term here, so that's going to be half of b over a, which is b over 2a squared. So we got x squared plus b over a x plus half of b over a is b over 2a. When we square that, that's b squared over 4a squared. But now since we added b squared over 4a squared, we need to also subtract it, but it's being multiplied by a when it's in here. So we're going to subtract b squared over 4a. Multiplying by a gives us a b squared over 4a squared. The a's cancel out, giving us minus b squared over 4a plus c. F of x is equal to a times, that's x plus b over 2a squared minus, actually, I'm going to look at this and actually, I'm going to say plus just because that allows me to put it all together. But if I see this, I can go for a common denominator of 4a, right, which means that I'm going to go negative b squared plus 4ac over 4a. Okay, and a slight modification here, f of x is equal to a, x minus negative b over 2a squared plus negative b squared plus 4ac over 4a. And we are now in this form. If we're in that form, then the vertex is at negative b over 2a, negative b squared minus 4ac over 4a. So that's our vertex. So vertex formula, now that we've completed the square in generic form, ax squared plus bx plus c, the x value of our vertex, or we can say h, is equal to negative b over 2a, and k is equal to negative b squared minus 4ac over 4a. So we now have a formula for the x and y values of the vertex if we're given a quadratic formula in standard form. So you go, oh, you may look at this and go, okay, h isn't too bad, negative b over 2a. In fact, that's easy for me to remember because there is only one vertex. There is only one x value that's going to give you the vertex. Anywhere else on our parabola, any other y value that's actually on our parabola is going to give us two x values. Right? There's going to be the one to the left of the axis of symmetry and the one to the right of the axis of symmetry. So the reason this is easy for me to remember is because the quadratic formula is negative b plus or minus the square root of b squared minus 4ac over 2a. If the discriminant is equal to 0, then you have just 1, 0, right? So where are we going to come out where we only have one x value? Well, when there's no discriminant, when there's 0 there, so negative b over 2a. If the discriminant is equal to 0, then we have a single x value. So h is equal to negative b over 2a. That's easy enough for me to remember. This other one throws me off because negative b squared plus 4ac over 4a, well, that's kind of like the quadratic, it's the discriminant. And I guess I should put that as, just to do it right, I have, how did I end up now? I ended up with b squared. So, okay, no, we're good there. Okay, just making sure. Well, we had oh, there's room. I'm like, that doesn't look right. And that's the problem. It's not the same as the discriminant. It's not the same as the quadratic formula. So you got to look for these things. And I realized what I did here was I went from plus here to a minus here, which is what threw it off. That's why it didn't look right to me. So, but not good. That's not a formula I'm going to remember. So what I can do is, rather than memorizing this, if I know h is equal to negative b over 2a, that's going to give me the x value of my vertex. To find the y value, I just plug that into the formula. Plug the x value in that I just came up with, that's going to give me y. So let's do an example with this. So I'm going to put this over here too. H is equal to negative b over 2a, and k is equal to this ugly thing, negative b squared plus 4ac over 4a. And we're going to use this to find the vertex. And remember, we can always find the axis of symmetry if we know the vertex. So let's say we have f of x is equal to 3x squared minus 7x plus 2. If I want to find the vertex, then I can say h is equal to negative b, negative 7, over 2 times a, which is 3, which gives me 7/6. And I've already got the x value. It's not pretty, 7/6, but I still have my x value. Now I can plug that into the original equation and find my y value. So we have f of x is equal to 3 times 7/6 squared minus 7 times 7/6 plus 2 is equal to 3 times 49/36. Make sure you put the multiplication there, otherwise it's 3 and 49/36, and that we don't want. So 3 times that, minus 7 times 7, so that's 49/6 plus 2. So we can multiply this by the 3 throughout there, so it is equal to 147 over 36. And I'm going to put this over 36 too, because that's going to allow me to combine it. So I'm going to multiply the top and bottom by 6, which gives me 294 minus 294 over 36. And then if I multiply the top and bottom of that by 36, then I end up with 72 over 36. 2 over 36. So now I can combine that. So I've got 147 plus 72 gives me 219. 219 minus 294 gives me minus 75. So minus 75 over 36. Well, that's not divisible by 2. It's not divisible. Is it divisible by 3? It is divisible by 3. That's right. So I can make it negative 25 over 12. And that's as far as I'm going to be able to go. So y is equal to negative 25/12. So our vertex is 7/6, negative 25/12. And there we go. Just to make sure, I'm going to grab my calculator and just make sure that I did my math there. So 147 minus 294 plus 72 is negative 75. Okay. I just wanted to make sure I didn't make any mistakes there as I was trying to do it in my head quickly. And there we go. So we found the vertex, and also the axis of symmetry is obviously x equal to 7/6, and there we're able to do it. So just to verify that we just have a little bit more to talk about. So we did that, so that's the vertex formula. Well, what about some additional characteristics of the graph of quadratic functions? So I'm going to read these right off of here just to make sure that I cover all these. First of all, if you want to find the y-intercept of a quadratic function, then find f of 0. So let me get this out of the way so I can write some of these things down. So if you want to find the y-intercept, set x equal to 0, so find f of 0, and that's going to give you some constant c, and that is your y-intercept. If you want to find the x-intercepts, then set your function f of x equal to 0 and solve. And that's going to, that'll probably include using either completing the square or the quadratic formula, or if you're really lucky, it'll be something that's a quick, easy factoring and you don't have to do either of those. So that's going to give you your x-intercepts. Okay? If b squared minus 4ac is greater than 0, so if your discriminant, what's under the radical in your quadratic formula, is greater than 0, then your x-intercept is going to be at negative b plus or minus the square root of b squared minus 4ac over 2a, right? So your quadratic formula. If b squared minus 4ac is equal to 0, then your x-intercept is simply going to be negative b over 2a. And if b squared minus 4ac is less than 0, there are no x-intercepts. So I'm going to say x-intercept and a, not applicable. Okay, there is no x-intercept if your discriminant is less than 0, because what do you have? If it's less than 0, you have two imaginary roots. Now realize that if it's greater than 0, you're going to have this. You're going to have two real roots. They may not be rational. Remember, they'll be rational roots if this is a perfect, if b squared minus 4ac is a perfect square. If it's not a perfect square, it's going to be an irrational root. But that's okay. We can still work with that. That just means that we would round to a certain number of decimal places. Or if we don't have to graph it and we're just giving an answer and it's not a word problem where we need a specific thing down to, a couple hundred, to the hundredths place or whatever, then we can actually leave it in the form negative 6 plus or minus the square root of 3 over 7 or whatever it turns out to be. So that's all valid. Okay? So we did that. So now let's look at quadratic models. So we're going to get into the model part, which basically just means application. We're going to get all that out of the way. So let's apply what we have learned. So we're going to start with this projectile motion formula. So the formula S of t is equal to negative 16t squared plus v sub 0 t plus s sub 0. Okay, so we have this formula. So negative 16, that is a constant based on the gravity of Earth. You've probably heard me mention previously 32 feet per second per second. That's acceleration due to gravity. So basically, if I drop an item, it is going to accelerate at 32 feet per second per second. So every second, its speed is going to increase by 32 feet per second. So you can say if I just if I hold this marker and I dropped it, and it can't fall long enough to do it here, but if there was a big hole in front of me, an abyss, and I was to drop this marker, it would start at 0. At 1 second, it would now be going 32 feet per second. At 2 seconds, it would be going at 64 feet per second because it's accelerating by 32 feet per second every second. So it's getting faster and faster and faster until we reach terminal velocity, but we're not going into that right now. So don't worry about that. Okay? So that's negative 16. So that's a constant due to gravity. And that's gravity on Earth. If you go to the moon, then the gravity constant is different. If you go to Mars, the gravity constant is different. And actually, this shifts a little bit depending on whether you're on the top of Mount Everest or if you're down in the Grand Canyon. Okay, even that being a distance further away from the core of the Earth and closer to the core of the Earth has an effect on that. So that's your constant due to gravity. T is your time in seconds. Since I'm going to say since launch, how your projectile got in motion, I don't know. But since launch, okay? That launch could be just dropping it. Or it could be tossing it up in the air. Or something shooting it out. But we'll just call it since launch. Okay? V sub 0 is initial velocity. So the initial velocity of the projectile. So if I was to drop this marker, my initial velocity was 0 because all I did was dropped it. So it started from rest. Whereas if I were to throw it down or toss it into the air, then I'm giving it some velocity to start with. So it's when it leaves my hand, how fast is it going? So that's initial velocity, and S sub 0 is the initial height. All right, I'm holding this up in the air. Well, that's about, if I put it about there, that's about 5 feet. So that's initial height in feet. And I should clarify with this that this is in feet per second per second. This is in that is in seconds. Initial velocity is in feet per second. And the initial height is in feet, because that's how this is all designed. And then S sub t is the height at time t. And that would also be in feet. Okay, so that defines this whole equation. So now that we have that, let's put it to use. So an object is launched at 112 feet per second from 75 feet above ground. Okay, so here's the thing. An object is launched at 112 feet per second from 75 feet above ground. Now the term launched means it's sent either up or forward. So generally in an upward direction, say. Launching is not dropping. If it was dropped, we know it was downward motion. But it's launched, so we know it's upward, and we know that upward is generally referred to with a positive number. Downward is generally referred to with a negative number. So it's launched at 112 feet per second, so that's our initial velocity. 112 feet per second. From 75 feet above ground. So 75 feet above ground, 75, not 7F. 75 feet above ground is our initial height. And now we still are wondering about T and S of t. Well, what do we need to do? So a question we're asked is, give the function. So basically plug these things into this function. At what time does it reach maximum height? So we want to come up with the function using these and determine at what time we reach maximum height. And while we're doing that, we might as well determine what that maximum height is. So we want the function. I'll say that over here. function, and we want maximum height and time of maximum height. So the first thing we're going to do is we're going to put this function together, which is simple. I'm going to just get this out of the way because that really doesn't matter. So S of t is equal to negative 16 t squared plus v sub 0, that's our 112, times t plus s sub 0 is 75. So now we have a quadratic function. S of t is equal to negative 16 t squared plus 112 t plus 75. We want to find the maximum height and the time that at which it reaches the maximum height. Well, maximum height, that's the maximum value. Our leading coefficient is negative, which means this parabola is opening down. So I'm just going to put that here, opens down. And the maximum value when it opens down is the vertex. So let me put this here, max value at vertex. That's where the maximum value is going to be. So now that we have that, we just need to find the vertex. I'm going to get these pieces out of the way because I don't need them now. So if I want to find the vertex, well, we need x is equal to negative b over 2a. So negative 112 over 2 times negative 16 is equal to, well, I've got negative and negative, so I'm going to get rid of those in the one step. So that gives me 112 over 2 times 16 is 32. So let's see here. So I can divide by 4. I may be able to divide by more than that, but I can't guarantee that at this point. Actually, I can guarantee that by this point. I can divide by 8. So 112 divided by 8, 8 times 10 is 80. 8 times 4 is 32. So 14. Okay, and 32 divided by 8 is 4. So we can go one step further and say, so I guess I could have divided by 16. So 7 halves, that's x. So x would be our time, right? The time, so I can say t is equal to 7 halves seconds, or 3.5 seconds. That's when I would reach the maximum height. What is that maximum height? Well, that's going to be y, that's s of t. So s of t is actually, we're going to do s of 3.5 is equal to negative 16 times 3.5 squared plus 112 times 3.5 plus 75. So if we go through that, let me grab my calculator. Then 16, negative 16, 3.5, let's square that. And multiplied by negative 16, that gives us negative 28.25. 112 times 3.5 gives us 392 plus 75. So I've got 392 plus 75 minus, wait a second here. That can't be right. Something's wrong with my 28.25. 3.5 squared times 16. There we go, that's better. Negative 196. always look at your numbers and see if they make sense. A quick look back at that said, no, there's no way that number is correct. I don't know what I plugged into my calculator. I must have hit a wrong button, and that gave me the wrong answer. So now, I have negative 196 plus 392 plus 75 gives me 271 feet. So at 3.5 seconds, we will hit our peak, or our maximum value, which is 275 feet. So we filled in the information that we were given, the initial velocity and the initial height. We then took that and solved for x. Well, I shouldn't say solved for x, but we found our x value of our vertex, or h, by taking negative b over 2a. Came out with the 7/2, or 3.5 seconds. And then we plugged that into this formula for t to determine our maximum value, the y value, or the k value of our vertex. And that's quadratic functions and models.